Okay, we're continuing with our simple gas laws. Avogadro's law relates volume and moles of gas. Amedeo Avogadro, the same guy who we refer to for Avogadro's number, he was actually born when our country was born. That's kind of cool. Died in 1856. He was the first one to formally state a relationship between a volume of a gas and amount of gas in moles or in particles. So what his law says is that the volume of a gas is proportional to the number of particles of the gas. It's not proportional to its mass, it's proportional to the particles. So here is the statement of, here I'll draw a box around it, of Avogadro's law. V1 over N1 is equal to V2 over N2. Volume is proportional to N. N meaning number of moles, and this of course is when temperature and pressure are held constant. So we count gas molecules or atoms by the mole. Equal volumes of gases are going to have equal numbers of molecules, and what the gas is doesn't matter. If you have 1 liter of nitrogen gas and 1 liter of krypton gas at the same temperature and pressure, they will contain equal numbers of moles. And that's a weird thing about gases, because we don't see things like that with solids and liquids, where what the substance is doesn't matter. Here's a graph. Found that the volume increased linearly with the number of moles. We extrapolate to 0, and this line predicts that 0 moles of gas would occupy 0 volume. Now, is that true? Yeah. 0 moles of gas, if there was no gas in there, it would have 0 volume, right? So let's do an example using Avogadro's law. A scale model of a blimp rises when it is filled with helium to a volume of 55 cubic decimeters. When 1.10 mole of helium is added to the blimp, the volume is 26.2 cubic decimeters. How many more grams of helium must be added to make it rise? Assume constant temperature and pressure. Now this is an Avogadro's law problem that is not just pull the numbers out and stick them in the formula. We have to think about this one a little bit. So if it's got helium in it and has a volume of 55 cubic decimeters, then it's going to rise. So they put 1.1 mole of helium in the blimp. The volume is 26.2 cubic decimeters. We want to get the balloon or the blimp to rise. That means it has to get to this volume. Okay? This problem is harder to decipher. It really is. So what we're trying to do is we're trying to get the blimp to be a certain volume. You can imagine we bought my kids one of these. We bought our kids one of these one year. You can buy them there. They're like a Mylar balloon, but it's blimp shaped and it's got a little motor on it, and you fill it up with helium. Well, if there's not enough helium in it, it's not going to float. It has to get up to a certain volume before it's going to float. So that's what we're talking about here. So we've got a volume, and this is a funny unit. We haven't used cubic decimeters, but that's okay. It's a perfectly reasonable volume unit. And here we have a mole of helium. So let's go ahead and make a table. We have our 2 conditions, 1 and 2, and we're looking for a volume of 55 cubic decimeters. That's a volume. And we have 1.10 moles of helium is going to give it a volume of 26.2 cubic decimeters. This would be N, the number of moles of gas. So we can calculate N1, the number of moles of gas that need to be in the blimp for it to be that larger volume, right? That's not going to be our final answer, though. But it's a step in the middle. I can never remember how they show Avogadros Law. Is it N on top or V on top? V on top? Okay, thank you. It doesn't really matter, but I want to try to be consistent. So this is what was on the previous slide, which I couldn't remember. V1 over N1 is equal to V2 over N2. We are solving for N1, especially if you're solving for a variable in the denominator. I would encourage you to cross multiply, get rid of the fractions so that you don't make a silly algebra mistake, which negates all your great understanding of the chemistry involved. So if we cross multiply, we're going to get N1 V2 equals N2 V1. And then we can divide by V2 on both sides. And we find that N1 is equal to N2 V1 over V2. So then we just plug those numbers in. It's 1.10 moles, and V2 is on the bottom. V1 is on the top. And V2 is on the bottom, 26.2. Someone else might make up this table and end up with 26.2 being V1. But then you'd be solving for N2, and the math would all work out the same. When we look at our units here, the cubic decimeters cancel each other out, and so they were not a problem at all. So we have 1.1 times 55 divided by 26.2. So the number of moles of helium that we need to have in that balloon are 2.30916 moles. How many significant figures does that number have? 3. It should have 3, so it would be right here. That's not our final answer, so I'm not going to round it yet. I'm just going to underline that third digit to remind myself that that one has 3. So they're asking, we've got this blimp, we put 1.1 moles in, how many more in grams do we have to add until it gets to the right volume? So here is the final number of moles. So from this and this number, we could figure out how many moles we need to add, right? We'll figure out the moles we need to add, and then we can convert that to grams. So the moles we need to, oh gosh. I know, I hate it when it does that. Oh man, I lost it. Okay, sorry. Wow, I'm losing it mentally too. It's because I'm so hungry. Yes. So N1 was 2.30916, is that right? Moles. So sorry, I touched the wrong place on my screen. That's how many we need to end up with. If we subtract what we have already put in, we get, this is the number of moles we need to add. That make sense? And if you need to draw pictures for yourself, draw pictures, okay? I'm not drawing a picture on here, but I've got a picture in my head of what's going on here. So then the question asks how many grams of helium is that? So then we're going to take, oh, and where would the uncertain digit in this number of moles be? Would be the 0 again, because there was uncertainty here, and when we subtract, it'll be there. So 1.20916 moles of helium. How do we convert that to grams? The molar mass of helium. So we're going to have grams on top and moles on the bottom. We look at the periodic table. 4 point, how many zeros? 2 zeros and then a 2? Okay. I can't quite see it from here. 4.002 grams per mole. Now we will round to our 3 significant figures, 9.24 grams of helium. In Chem 3A, we would just ask you to calculate the number of moles in the blimp at 55 cubic decimeters. In Chem 1A, we want to know, can you think? Do you understand? Can you put these concepts together, sometimes in a way that you haven't seen before? Any questions? Yes?
The answer is 4.8.
Is it? The answer is 4.83. I did it wrong? Oh, yeah. Thank you. I had the 2.309 in my calculator still. Oh, good grief. 2.30916 minus 1.1 times 4. Yes, yes, yes. Thank you, thank you. So, how about 4.84? Is that better? Yeah, just, shout it out. You're not going to make me feel bad. I make mistakes all the time. I'm just bluffing my way through life. I'm doing a pretty good job of it, though. Yeah, okay. Did I screw up anything else? Then we get to what's known as the ideal gas law. And this is like the parent gas law, because all the others are all wrapped up into this one. So this law is affectionately known as PIV-NERT. If you were going to try to pronounce that, there's no vowels in it, but it would be PIV-NERT. So PIV-NERT is what we sometimes call it. PV equals nRT. And we can see these other 3 laws in here. If we rearrange this and solve for V, we see that V equals nRT over P. If we hold the number of moles of gas constant and the temperature constant, we see that the volume is proportional to 1 over the pressure, and that is Boyle's law. If we take this rearrangement and hold N and P constant, we see that the volume is proportional to the temperature, and that's what Charles discovered. If we look at this and hold the temperature and the pressure constant, we see that the volume is proportional to n, and that's Avogadro's law that we just looked at. So all of these laws are all wrapped up inside of the ideal gas law. There's another one that your book doesn't discuss separately, and that's Gay-Lussac's law, which relates, I think it's temperature and pressure. I can't remember. I think it's good to know these people's names. They contributed significantly to chemistry. I am not going to quiz you on which one of these laws is Boyle's law. I don't think that's important. I think what's important is that you know the equations and know how to use them. And I'll show you something that I think is cool, and occasionally I find a student who thinks it's cool. You can actually derive all of those equations really quickly from PV equals nRT. If you take P1 V1 equals N1, R doesn't get a 1 because it's a constant. We'll talk about what it is in a minute. T1. And if I divide this by P2 V2 equals N2 R T2, that is still an equality, right? Because PV equals nRT, and so even though it looks like I'm dividing each side by something different, what I'm dividing it by is equal to each other. And so this is still an equality. R is the ideal gas constant that we'll talk about in just a minute. It's a constant. It doesn't change. And so that would cancel out. And from this point, you can look at whatever problem you have, and anything that's not changing, you could get rid of. So if the number of moles of gas wasn't changing, N1 would be equal to N2. Even if you don't know what it is, they would cancel out. And if the temperature was constant, T1 would be equal to T2. And that would leave us with P1 V1 is equal to P2 V2, which is Boyle's law. You can get any combination that way. And I'll show you another one that's really useful. Let me just go back. This one, with pressure, volume, and temperature changing, is often called the combined gas law. Another way to write that would be P1 V1 over T1 is equal to P2 V2 over T2. This is a combination of Boyle's law and Charles' law. So the amount of gas is staying the same, but the pressure, the volume, and the temperature are changing. And you may see some homework problems like that. So how you remember the gas laws kind of depends on how your brain works. If you're a person who likes to understand the process and then apply it to lots of things, and you're good with algebra, you may want to just remember PV equals nRT and know that you can figure out whatever combination you need. If you're a person who doesn't think that way, you may want to just memorize the individual gas laws, and that works fine too. So whatever works for your brain. Yeah, there's something missing from my slides here. Well, we'll stick it in here. What is R? Okay. R is the ideal gas constant, and it is 0.082. Well, do they do 8206 or do they do 821 in your book? For the ideal gas? 06? Okay. Did I have it on there somewhere and skip it? Oh, how did I do that? Okay. Well, I am losing my mind, and yet I'm not losing my mind. I accidentally skipped this slide, but I'm not losing my mind because here's the ideal gas constant. Good grief. So I skipped to the table. Blah, 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 blah. R is the ideal gas constant. So the value of R depends on what units we use for pressure and volume. We always use N for, N is always in moles, and temperature is always in Kelvin. But if you use different pressure and volume units, you could end up with a different constant. The constant we're going to use is this one, using liters and atmospheres. And so R is equal to 0.08206. And the units look pretty funky, but they are that way so that they cancel out. This is just a constant. So liters times atmospheres divided by moles times Kelvin. For the ideal gas law, it does matter what units you use for pressure and volume. For those other laws, Boyle's law, Charles' law, we used cubic decimeters, and that was fine because they cancel out. In the ideal gas law, you need to use the units that are in the ideal gas constant. Okay? Okay, we did that already. Now we'll do this one. So always read through the whole problem. A steel tank has a volume of 438 liters and is filled with 0.885 kilograms of oxygen. Calculate the pressure of oxygen at 21 degrees Celsius. Now, reading that, you may recognize that nothing is changing. You see that? The other problems we've had so far, there have been two volumes or two pressures. There have been two of one of the quantities. And then we've had changing conditions, and that's where you really need to make a table. Some students, find it a little challenging to determine, am I using one of those simple gas laws or am I using the ideal gas law? Which one am I doing? And so if you take the make a table approach with this, that'll work out fine too. We'll just find that we only have one row instead of two rows. So I'm going to make a table just to demonstrate how that works out. So I'm going to pretend that I don't recognize that there's only one set of conditions. So I'll just go through like we've done before. Write down the numbers with their units. So 438 liters, that's a volume. 0.885 kilograms. What does that correspond to? It corresponds to moles, and yet it's not moles yet, is it? So we're going to need to convert that one. So we'll have to come back to him. 21 degrees Celsius. What do we need to do to that? We need to convert that to Kelvin. So we're going to add 273, so we're going to end up with 294 Kelvin. We've gotten through all the numbers, and there was no second row. It's okay. Just erase the second row. We don't need it. But now I've got my numbers labeled, so that's kind of nice, right? So if there's only one set of conditions, the law to use is going to be PV-NRT, PV equals nRT. And it says calculate the pressure. So we want to take this law and rearrange it so that we get P equals something. So we'll divide by volume on both sides, and we'll end up with, I'll just write it over here. We end up with P is equal to nRT over V. Now we do need to be careful with our units. The units on the ideal gas constant are liter, atmospheres, moles, and Kelvin. Liters is fine for volume, but this is not good. This is not acceptable. So we need to change this into moles. They tell us it's this many kilograms of oxygen. So 0.885 kilograms. I first need to get that into grams. I've got kilograms on the bottom, grams on top. Kilo means 10 to the third. I put what the prefix means on the other side of the line from the prefix. So now I've got grams, and then converting from grams to moles is the molar mass. So I get my units in first. Oxygen is O2, so it's 2 times 16, it's 32, 1 mole. 0.885 times 1,000 divided by 32. So 27.65. We want to have, this is going to have 3 significant figures. I'm going to carry along 2 extras to avoid rounding errors. 27.656 moles. So now we've got everybody with the right units. 27.656 moles, that's N. R is something you need to memorize. 0.08206 liter atmospheres per mole Kelvin, very messy units, times the temperature in Kelvin, 294 K, and all of that divided by the volume, which is 438 liters. .656 times 0.08206 times 294 divided by 438. How many significant figures should this pressure have? 3. So it's going to be 1.52. 1.52. What unit? Atmospheres. Did I get the right number that time? Okay. Let's look at these units real quick. We get into a lot. We've got fractions within fractions. But looking at all these guys in the numerator, we've got moles canceling moles. We've got Kelvin canceling Kelvin. Then what we've got left in the numerator is liters times atmospheres. These liters cancel those liters, and we end up with atmosphere as our pressure unit. Any questions? This one's fairly straightforward, but the twist is they gave you the mass of oxygen instead of the number of moles.